This is a course on nonlinear finite elements in solid mechanics, and we will mostly be dealing with problems where the degrees of freedom at a node are the displacements, and the behavior of the material can be nonlinear. What I'll do in this first class is introduce, firstly, recapitulate a few things that we have already done in a basic finite element course, and secondly introduce a set of notations, especially tensor notations that we are going to use off and on throughout this course in order to frame the finite element equations. The first uh, equation that we have encountered in our finite element courses, and indeed in course on elasticity, is the equilibrium equation. So this equilibrium equation in terms of stress, also written as sigma ij comma j plus bi equal to 0, where bi is the body force, volumetric body force, which is force per unit volume, and the stress is specifically the Cauchy stress, and we will later distinguish between Cauchy stress and the other kinds of stresses, but uh, we have learned about this equilibrium equation only in our courses on elasticity and finite element, and um, we have encountered only one kind of stress so far, which is the Cauchy stress. Soon we will encounter other kinds of stresses as well. Now, this is valid within all points inside a volume of a body, which we denote by omega. And on the boundary of the body, we have two kinds of boundary conditions specified. So there's a part of the boundary which we will call delta omega t, on which tractions are specified. So these tractions that are specified are given by the Cauchy relation Ti equal to sigma ij nj. Again, if you change the kind of stress that you are dealing with from Cauchy stress to some other kind of stress, this will also change, but we will come to that later. This is what we have learned so far. So the tractions, the applied tractions, Ti are the tractions that are applied on this part of the boundary, and they are related to the stresses right next to the point of application of the traction by sigma ij nj, where n is the outward normal at the point of application of the traction. So this is a boundary condition that is applied on delta omega t, and then you have another part of the boundary which we call delta omega u, which has displacements applied on it. So for example, this part of the boundary has displacements applied on it, and we have the condition that one of the two boundary conditions, either this or this, must be applied at each and every point in the boundary, and there should be no point on the boundary on which both are applied. So this is the description, the strong form description of a problem in linear elasticity. This is of course not complete without the constitutive equation and the strain displacement relations. So again, the strain displacement relation that we have learned is epsilon ij equal to half del ui del xj plus del uj del xi, which is also written as half ui comma j plus uj comma I. This is how we write it. This has to be valid. This is a strain displacement relation valid on each and every point inside the volume. And all this has to be supplemented with the constitutive equation, which is in our case, what we have learned so far in our basic courses, is sigma ij equal to Cij kl epsilon kl, which is a constitutive equation for linear elasticity. In particular, in many cases, we have assumed that Cij kl is an isotropic tensor, and we have dealt with isotropic linear elasticity. So this completes our uh, description of the problem in the strong form, and we have as many equations as there are variables. So the number of variables, as you might know, sigma ij constitutes 6 variables, epsilon ij constitutes another 6 variables, and ui, the displacements at each and every point, another 3 variables. So that's 15 variables in total. Hooke's law gives you 6 equations. This gives you 6 equations, and then another 3 equations come from the equilibrium equation. So we have 15 equations and 15 unknowns, which completes the problem, provided you have specified these boundary conditions also properly. So that's what we have dealt with so far. We are going to relax many of these equations. We are going to relax, as I said, we are going to talk about different kinds of stresses, which will lead to different kinds of boundary conditions. We will also relax the assumptions that have gone into derivation of this small strain tensor, and we will show that strain can be defined in many ways, and each of them give rise to equation that is more complicated than what you see on the screen. We will also be looking at constitutive equations which are not as simple as the generalized Hooke's law. So in the generalized Hooke's law, the CIJKLs that you have are constants which have to be determined from experiments or other kinds of simulations, like say molecular dynamics. But we will be considering situations where the constants governing the stress strain relation, constants in the constitutive equation, are functions of displacements or strains, and therefore the stress strain law itself is nonlinear. So so what we have here is material linearity. This is material linearity. So we have a linear material because the CIJKLs are constants. So we will get rid of this assumption later. And here we have what is known as geometric linearity. Something that will become clearer once we look at more generalized forms of the strain tensor. So we will be relaxing both the conditions of geometric linearity and material linearity. Now, in doing finite element discretizations, we generally do not go by the strong form of the equations, but we frame a weak form, which is also known as a virtual work principle. Now, the virtual work principle, we will deal much more with this. So the virtual work principle simply says that the internal virtual work is equal to the external virtual work. So this is the virtual work done by the body forces acting at each and every point on the volume, and the surface tractions working on delta omega t. So this is the virtual work done by the external loads, whereas this is the internal virtual work which is stored in the body. Now, delta U is a virtual displacement which is an arbitrary function of position, except that this has to be 0 wherever U is specified. That means specifically on this part of the boundary where U is specified, delta U has to be equal to 0. That is the only condition that we impose on delta U, and based on that delta U, we calculate delta epsilon using this. So delta epsilon is the strain tensor, small strain tensor calculated, the virtual small strain tensor calculated using the virtual displacement field, in exactly the same way as the real displacement field is used to calculate the real strain, small strain tensor. So this virtual this virtual strain uh, does work on the virtual stress. So to give you the internal virtual work, and that has to be equal to the external virtual work. This is what we use. And in case of linear elasticity, this principle follows directly from the principle of minimum potential energy that elastic bodies are known to abide by. So elastic bodies obey the principle of minimum potential energy, and if we use the principle of minimum potential energy, we actually write the potential energy of this of an elastic body under surface tractions and displacement boundary conditions and minimize the energy, we get to this virtual work principle. Okay. The virtual work principle itself is actually an identity. So if you start from the left, you will reach the right, provided on the way you use the equilibrium equation, the strain displacement equation, and the constitutive equation. Sorry, not the constitutive equation, but the strain displacement equation and the equilibrium equation. If you use it correctly, then starting from the left, you can actually reach the right. So what we have written is actually an identity which rests on the fact that we have chosen delta u to be a function which satisfies this condition. So as long as you choose this kind of a function, which is known as an admissible function, so if you use an admissible displacement which leads to this virtual strain tensor, you will get internal virtual work equal to external virtual work as an identity. So this is the starting point of our finite element formulations in case of linear elasticity. This will also change as we go along with nonlinear finite elements, but we'll come to that later.